Hello and welcome to Cosmic Veil. I am so glad you are here. Whether you have had a long day, a busy mind, or you simply love drifting off to the science of the stars, I made this just for you. Tonight, you and I are going to look deep into the cosmos to uncover a very strange truth in physics, why light itself has a strict speed limit. But before I point the telescope, I would love to know where on Earth you are listening from, and what time is it in your corner of the world. Are you resting under bright city lights, or somewhere far out, quiet and dark? Maybe holding a warm cup of tea. If you enjoy our quiet nights exploring the galaxy, I would be truly grateful if you liked and subscribed to the channel. It helps other stargazers find their way to my observatory, and it means I can keep making these soft, starlit journeys across the universe just for you. Now, I genuinely hope my astronomy talk is not too interesting tonight. If my voice accidentally keeps you awake, at least you will leave knowing a little more about how our incredible universe operates. Not a bad trade, right? Settle in, close your eyes, and let's take a slow, thoughtful journey into the story of starlight and why it is in such a frantic hurry. Light is something we all assume we completely understand, right up until we actually have to try explaining it. You flip a wall switch, and there it is. It floods your room, lets you see your cat's judgmental stare, and makes your phone screen glow long after you swore to put it away. But what is it really? Is it a wave, a tiny particle, a phantom, or a cosmic messenger running on a very tight delivery schedule? The short answer from an astronomer is yes, and also sort of. Let's take a nice slow walk through what light truly is. Because before you and I can understand its strict speed limit, we first need to figure out what is actually doing the speeding. First, let's look at photons. They are the tiny, energetic packets that make up light. Picture them as tiny couriers zooming across deep space at the absolute fastest speed the universe allows. But these little messengers are very strange. They are not physical particles like marbles or grains of sand. They have zero mass, they never ever rest. And they completely ignore normal physics. Now, here is where my job gets fun. Photons are also waves, just not the kind rolling across an ocean beach. They are electromagnetic waves. Vibrations of electric and magnetic fields, oscillating at perfect right angles to each other and to the exact direction they are flying. I know that sounds like abstract math, but the picture is quite beautiful. Two distinct fields dancing through the dark vacuum together, locked in perfect rhythm. These waves do not need a medium to travel through. That is important. Most waves, like sound, water, or even waving at a friend across the street, require some material to move through. Sound always needs air. Ocean ripples obviously need water, but light just goes. It shoots across the empty vacuum of space without a single problem. That is why my telescope can see the sun 90 million miles away. Its light crosses the absolute emptiness of space to reach us without making one rest stop. And starlight does not just come in one simple flavor. The light we observe, known as visible light, is just a tiny fraction of the electromagnetic spectrum. Imagine a grand piano stretching out for miles. Visible light is just a few keys right in the middle. On one far end, we have radio waves, long, lazy signals that can stretch out for absolute miles. On the opposite side, we find gamma rays, sharp, high-energy bursts that punch through almost anything, usually born deep inside exploding supernovas and violent nuclear reactions out in the dark. In between those extremes sit microwaves, infrared from your television remote, ultraviolet, which gives you summer sunburns, and X-rays, which easily scan your bones but never find your lost telescope lens caps. Despite all these major differences, all these forms of light share the same vacuum speed, about 300 million meters per second. Just under 300,000 kilometers every single second, a number so massive it honestly feels like complete nonsense. It's like asking the night sky how fast, and the universe replies, yes. To put it in simple, sleepy terms, if a beam of light were a runner, it could lap the entire Earth over 7 times in one single second. Not bad for a wave with no legs, but here is another detail I observe all the time. Light does not always travel that fast. Out in the empty vacuum, it has a clear track with zero cosmic traffic, but passing through telescope lenses, water, or dense diamond, it actually slows down. Not because it grows tired, but because it interacts directly with the material's atoms. It is somewhat like pushing through a crowded observatory. You are still heading toward the door, but there's a lot more bumping and dodging involved. That sudden speed drop is what causes refraction, the actual bending of starlight when it transitions from one transparent medium into another. It is why a straw looks snapped in a glass of water, or why a polished diamond catches the light so brilliantly. It's all about how that starlight's journey gets delayed, rerouted, and scattered. But here's the real twist. Even when light slows down through dense space dust or glass, single photons still keep their absolute speed between atomic bounces. They just take a scattered path. Picture trying to speed walk through a busy observatory floor full of excited tourists at midnight. Let's pause, you and I, to look at color. When I gaze at a rainbow, a heavy glass prism, or an oil slick in a puddle, I just see starlight splitting into scattered wavelengths. Every visible color waves differently. Deep red stretches out long, while violet vibrates short and fast. Yet they are all just photons, electromagnetic waves from distant stars, vibrating at completely different frequencies. Your eyes contain special cone cells tuned to catch exact ranges of those waves. That brings you color. That apple isn't really red, it merely reflects the specific cosmic waves we call red while absorbing the rest. Color is really just your brain guessing, based on the light vibrations hitting your retinas. And as if the cosmos wasn't strange enough already, a photon has absolutely zero rest mass. Unlike you, me, or your judgmental cat, it needs absolutely zero extra energy to travel. It always moves, it simply has to. If a photon stopped, it wouldn't just pause its journey, it would vanish entirely. It's pure motion or absolute nothing. That is pure astrophysics. So we have these massless energy packets acting like particles and waves, speeding across the void, interacting with atomic dust, bending around corners, and reflecting off solid surfaces, carrying the gift of sight and color right to our observing minds, and we are just getting started. Tonight, as I watch the sky, picture light as a restless traveler built from nothing but pure energy. Never pausing, never sleeping, constantly revealing the shapes of our universe. It shows me distant stars, the faces we love, and my astronomy books. And it follows the strict cosmic rule, hitting an exact speed it can never break or fall behind. Light isn't just a tool for vision. It's how the cosmos whispers its age. You and I are going back in time now. Long before we astronomers had orbital satellites and lasers to probe space, picture a quiet world lit completely by fires and stars. Tracking something as fast as starlight back then wasn't just hard, it sounded completely absurd. For most of human history, stargazers thought illumination crossed space instantly. It simply existed. You struck a match, the dark vanished. The sun breached the horizon, turning fields golden. No waiting, no travel time. It felt completely obvious to early sky watchers. Ancient Greek thinker Empedocles actually guessed light had a strict speed limit, but fellow scholars just laughed his theories away. Aristotle, whose heavy cosmic opinions had the sad habit of sticking around for centuries, declared light was instant, shutting down the debate completely. Case closed. But then Galileo finally looked up. Galileo wasn't the kind of observer to just blindly trust the old academic authorities. He loved dropping weights and pointing his primitive lenses at the moon. By 1638, he attempted the most beautifully naive experiment to clock light's speed. His basic plan was simple. He and an assistant took covered lanterns out to dark hilltops spaced roughly a mile apart. Galileo would open his lamp, and the moment his partner saw the beam, he'd uncover his own. He planned to time the gap between sending the beam and catching the return flash, beautifully ambitious. Just human reaction time alone eats up a quarter of a second. Meanwhile, photons cross a mile in under a 10,000th of a second. It's like timing a speeding bullet using a sundial. Still, I deeply respect his ambition. Unsurprisingly, Galileo realized that if light travel took time, it moved far too fast for his eyes to catch, but at least the inquiry began. Decades later, a fellow astronomer named Ole Römer would accidentally solve it in 1676 by aiming his glass at deep space. The distant moons of Jupiter. Römer was charting Io, one of the gas giant's moons, watching it orbit out there like a giant, flawless cosmic clock. While carefully recording the exact moments Io vanished behind the planet and returned, he caught something odd. The eclipses kept shifting. Sometimes the moon emerged late, other times it arrived too early. It seemed baffling, but Roma had a stroke of genius. What if Earth, not the moon, was shifting? So what do you and I make of this? Maybe Earth drifted further from Jupiter, forcing Io's light to travel millions of extra miles. And suddenly, the idea of light having a measurable speed took real shape for us astronomers. From those celestial timing gaps, rumors estimated light needed 22 minutes to cross Earth's orbit. We now know that cosmic distance is roughly 186 million miles. Incredible work, honestly. He lacked modern atomic clocks or exact orbital maps, so his math wasn't perfect, but it completely shifted our universe. It proved that starlight takes time to reach my telescope, not much, but enough. By the early 1800s, a physicist named Yplet Fizeau brought this cosmic mystery down to Earth. You and I will examine his setup: a light beam, spinning wheel, and a distant mirror. Here is how he did it. He aimed the beam through a gap in the wheel's teeth, letting it shoot to that distant mirror and bounce right back. When that wheel spun slowly, the returning beam easily slipped through the exact same gap, staying fully visible. But spin it faster and the returning light smashes into a solid tooth, disappearing completely. By carefully tweaking that spin, Fizeau hunted for the exact moment the light beam vanished into darkness, proving the beam took just enough time to hit the mirror and return, while the wheel shifted half a notch. By taking the exact distance and rotation speed, he clocked light at 193,000 miles per second, strikingly close to modern physics, especially for a guy relying on simple gears, mirrors, and raw genius. Decades later, another scientist named Leon Foucault stepped up, replacing those clunky wheels with spinning mirrors. This single change pushed the precision perfectly. He proved light doesn't just have a fixed speed, it actually drags, moving noticeably slower through water than empty space. A massive hint for astronomers like me that matter alters light velocity. But the most legendary name in this whole quest is Albert Michelson. Late in the 1800s, Michelson grabbed Foucault's mirror trick and pushed it to an obsessive level of precision nobody thought possible. He built massive vacuum tubes, perfect mirrors, and flawless timing to catch data that entirely floored the scientific community. He bagged the Nobel Prize in Physics in 1907, the first American to do so. Not a bad prize for simply chasing photons across a dark room. Today, my observatory uses better toys: lasers, atomic clocks, satellites. We even anchor the meter to light speed. Since 1983, a meter is just officially defined as the exact distance. Light travels in a precise fraction of time. Essentially, we flip the script. As astronomers, we no longer measure light's cosmic speed. We use it as the ruler for everything else. Yet it all began with stargazers watching moons, spinning brass wheels, wondering if the cosmos moved slower than it seemed. And for me, that is the quiet beauty of physics. This cosmic limit isn't just data. It is a story of obsessed minds, flawed telescopes, and beautiful persistence. It is a legacy echoing through observatories and deep space orbits. Proof that the fastest thing in the cosmos could never outrun our basic human wonder. So, now that you and I have chased this photon across the centuries, let's ask the heavy question that actually keeps us stargazers awake late into the night. Why doesn't light move faster? It feels entirely arbitrary. Why exactly 299 million meters per second? Why not a clean 300 million, or 500 million, or just infinite? Why does starlight, this ghostly, massless pure energy, have to obey any cosmic speed limit? To grasp this, we have to gaze deep into the most mind-bending, beautiful corner of the physical universe, the laws of electromagnetism. More specifically, I want to introduce you to a brilliant genius named James Clerk Maxwell. In the 1860s, Maxwell gathered every piece of data we had on electricity and magnetism. Think Franklin's lightning rods, Faraday's magnetic coils, and he distilled them all into 4 gorgeous formulas. Today, we blandly call them Maxwell's equations. They perfectly map how electrical and magnetic forces interact and ripple. Don't worry about the heavy math, we leave that at the observatory door, but here is the truly magical part. When Maxwell fused these equations, something profound appeared. They predicted an entirely new ripple, an electromagnetic wave. Born the exact moment that electric and magnetic fields vibrated in perfect cosmic harmony. And this strange energy wave would always hold one speed. Punching in the basic constants of nature, he solved for its velocity. The result was 299,792,458 meters per second. Maxwell froze. Looking at his equations, he found a fundamental speed hidden deep within electricity and magnetic forces. The incredible part, that exact figure matched our best astronomical measurements for light speed. It was no accident, it was a total revelation. Light, he suddenly realized, was an electromagnetic wave. A ripple of pure energy, cruising through the void at a pace set by the very fabric of the cosmos itself. You and I really need to let that sink in. This velocity is not a random habit. It is baked into the math governing our entire reality. The cosmos did not just spin a dial and pick that number. Our universe physically had to work this exact way. Because electric and magnetic fields exist everywhere, light is forced to travel at this specific pace. That explains part of the mystery. Light moves this way because it is the only possible speed for an electromagnetic wave in outer space. Any faster or slower in astrophysics, as I know, it shatters, but let us look a little deeper. Why can nothing beat that speed? After all, down here on Earth, speed feels like more of an optional choice. If you drive 100 kilometers per hour, you can easily push it to 110. With starlight, there's no upgrade, just an absolute hard stop. To see why, we turn to a physicist you have definitely heard of, Albert Einstein. In 1905, he published his special theory of relativity. It changed my field overnight. A core pillar of special relativity comes down to this. The speed of light in a vacuum never changes for any observer, regardless of their motion. It sounds mild, but it is pure madness. Picture a train moving at 90% light speed. Totally impractical, but perfect for a thought experiment. You click on a flashlight. You might assume that beam looks faster to an astronomer watching from a stationary platform. After all, the train is hurtling forward, and you just added a beam of light. But no, both you and I on the platform would measure that passing beam at the exact same velocity. 300,000 kilometers per second. Not a single fraction more. To make this work, reality itself must literally bend around this rule. Time stretches, length shrink, and mass grows. The cosmos alters its own ticking clock so that no observer ever sees a photon speed up or slow down. If you piloted a starship toward light speed, you would hit a wall. As you accelerate, your mass climbs. Not like putting on weight, but in the sense that you demand vast amounts of energy just to push slightly faster. As your ship nears light speed, its mass approaches infinity. You would need infinite fuel to reach it, and infinite energy is impossible, even for the boldest cosmic traveler. So no matter how hard you push the engines, you can only get close. You can chase a starbeam but never catch it. This is why light speed is more than just a measurement. It is the absolute ceiling for how fast information or physical matter can cross our galaxy. A fundamental boundary woven into space itself, but here is a comforting thought. Without this limit, the cosmos would unravel. The basic rule of cause and effect would entirely collapse. Through my telescope, I could see an explosion before the star even died, bending time backward. It would mean pure chaos, endless paradoxes, and a nightmare for modern physics. Instead, the universe shields us from that madness with this beautiful cosmic cap. It keeps the night sky ordered, steady, and calm. So when you and I look through a telescope or simply watch a sunset, remember, those ancient photons didn't just randomly arrive. They followed a strict law carved into the very bones of astrophysics. A law declaring this fast and no faster, a boundary giving our universe its structure, stability, and breathtaking beauty. Light peaks there because it must, not from weakness, but because it is utterly perfect exactly as it is. Bound to a constant that keeps time marching forward, keeping reality intact. And it lets astronomers like me study the heavens in a way that actually makes sense. Honestly, for something crossing the void at nearly 300,000 kilometers a second, it is a profoundly graceful pace. Einstein had this amazing gift for flipping astrophysics upside down, making the universe's quiet whispers feel so completely obvious in hindsight. He was just the first person to truly listen. When he published Special Relativity in 1905, he completely rewrote the laws of physics. His equations centered around one very bold claim. Every night I look at the stars, I rely on one absolute truth: light speed in a vacuum never changes, never. A beautifully locked number for everyone, everywhere, always. As you drift to sleep, that might sound simple, but it shatters our cosmic understanding of motion and time. Picture yourself floating peacefully through deep space in a ship. You're holding a simple flashlight, you click it on. A soft beam races ahead of your vessel at, say it with me, exactly 299 million meters per second. Now picture another stargazer, maybe your co-pilot, soaring past you at half the speed of light. Through their observation window, you and your quiet vessel are just a sudden, glowing blur. Yet when their instruments track that exact same light beam, they don't clock it moving even a fraction faster or slower. Their sensors read that exact same massive speed. To us astronomers, that is profoundly, beautifully strange. Down here on Earth, normal speeds add together. Strolling down a moving airport walkway, your pace simply combines with the steady glide of the mechanical belt beneath your feet. But starlight is different. The platform moves, the observer moves, the celestial source moves, yet that radiant speed stays perfectly locked for everyone involved. So what is the universe hiding? Einstein gave us a beautifully unsettling answer. Light speed doesn't change. Instead, the universe bends everything else. Space-time, the subtle flow of moments, even physical dimensions. It all flexes and warps just to protect that one sacred, unchanging cosmic rule. Let's explore these starry consequences together. First is time dilation, an absolute favorite for both astrophysics students and dreamy science fiction authors. The faster you travel, the slower your clock ticks compared to a quiet observer sitting still. Not an illusion, but a physically measurable truth. Imagine launching an orbital craft hurtling at 90% of our absolute speed limit. Inside your cabin, reality simply feels perfectly normal. You log star charts, sip warm tea, and read quietly. But returning to your home planet, you discover the Earth has aged far more rapidly than your tiny, speeding vessel. Years, maybe decades, you took a brief starlight journey, while your pale blue dot aged completely. As scientists, we don't just leave this in textbooks, we actually measure it daily. Particles called muons, born high in our atmosphere from deep space cosmic rays, vanish in mere microseconds. Yet plummeting at near light speeds, their tiny internal clocks drag. They survive much longer, giving our observatories just enough time to detect their quiet impacts. Time quite literally stretches out for them. Then comes length contraction, the equally bizarre sibling of this temporal bending. Cruising at those incredible velocities, everything along your flight path physically compresses. We aren't talking about optical tricks, it is pure structural reality. Your glowing ship would tangibly measure shorter against the dark starry background. Now, before you picture your body squishing uncomfortably, relax. We astronomers know this strange compression only matters as you approach that ultimate cosmic boundary. For terrestrial trips in cars, jet planes, or even morning runners, the physical shrinking is incredibly tiny, practically invisible. But approaching starlight speeds, the universe itself becomes wonderfully squishy. Next is the relativity of simultaneity. A dense academic phrase, I know, but a wonderfully peaceful stretch for your imagination. It proves that two cosmic flashes happening simultaneously for one quiet stargazer might look totally unsynchronized to a different astronomer flying past them through the dark. Picture a sleek transit train gliding quickly along its rail. Inside its very center, a soft bulb flashes warmly. To the traveler sitting calmly inside, those gentle beams strike the front and rear walls at the exact same instant. Yet for an observer waiting on the station platform, that glow hits the back wall first, as the speeding front edge constantly escapes the expanding light. Both perspectives are flawlessly true. Space and time aren't rigid. They are deeply flexible, local, and personal. All this lovely, bizarre cosmic behavior, fading distances and shattering timelines, exists solely to defend the universe's ultimate speed limit. Almost like the cosmos studied this single velocity and whispered, "The rest can warp, but this rule holds firm." A truly unbreakable, silent celestial treaty. To keep those starry photons racing at a perfect pace, reality sacrifices its own rigid shape in exchange. This elegant balance preserves the flow of cause and effect, and truthfully, that brings a profound, quiet comfort. This universal barrier defends the very concepts of past and future. Because starlight has a top speed, our knowledge of the universe does too. You cannot witness a distant supernova erupt before it physically ignites, nor can you whisper a warning back through history. That glowing boundary keeps reality sensible, structured, and beautifully neat. Without it, existence would completely unravel. Theoretically, you might shatter planets before aiming a weapon. You could read a transmission from deep space before it transmitted. Paradoxes would flood the dark sky. So instead, as you and I stargaze, the cosmos simply whispers, "No, let's keep things peaceful." The universe demanded order, a maximum speed limit completely sacred. For us studying the cosmos, this is exactly where Einstein's genius shines brightest. He didn't just map out light speed as some cosmic sailing. He proved it is the actual foundation of reality, the very framework holding up space and time. Today, satellites use those equations so your phone knows you aren't lost at sea. Down in the labs, physicists rely on them to steer tiny particles at truly mind-bending speeds. And at the observatory, I use them to decode faint whispers from distant galaxies. Everything we know rests on this strange, beautiful truth. Light has an absolute speed limit, and it stays the exact same for all of us. So when you watch a sunbeam stream through your window, or catch a beacon flashing in the night, take a quiet second to appreciate it. It is not just warmth, it is the delicate, hidden geometry of space and time. A silent agreement written in pure photons, no matter how fast you travel across the void or how far away you drift. It always arrives at that exact same pace, steady, unbroken, and perfectly on time. You and I have spent some time exploring what light is and how we measure it. And we have seen why the cosmos demands such an exact, unbreakable speed limit. Now let us step back from the telescope for a second. Let us see how this boundary shapes reality itself. Because once you accept that photons can never move faster, the effects on our universe become massive and honestly, profoundly beautiful. We can start with the most basic rule of astrophysics, the flow of time. Not the ticking hands on your wall, but the deep mechanics connecting events, memories, and cause. This physical limit gives time a rigid skeleton. It builds walls around what can actually happen. It acts like a cosmic rulebook. You can only link two stars if light has enough time to cross that gap. In astrophysics, we map this out using something called a light cone. It is just a simple, elegant way to chart out which pieces of the universe are bound together. Picture standing outside under the night sky. You strike a match. That tiny little flare throws out photons in all directions. The absolute farthest anything can ever react to that flame is completely trapped by how far its glow can stretch from that exact second. If my telescope was set up 100 light years away, I would not even see that spark for an entire century. Now flip that around. Picture yourself in that dark field, waiting to witness a supernova. The only cosmic events that can actually reach you tonight are the ones whose light has already crossed the void. That creates your past light cone. It holds every single event that could shape your present. To an astronomer, this is not just math. It is the hard line between reality and fiction. If a star explodes outside that boundary, it is not just distant in space. It is entirely out of reach in time. No radio wave, no gravity ripple, absolutely nothing from that explosion can reach my instruments yet. For now, it simply does not exist, not until the photons arrive. This one concept defines my entire field of study. It means instant messages do not exist. There is no grand clock syncing the galaxy, and no universal present moment. Everything is intensely local. My present moment is different from a star system light years away. This speed limit is the only rule keeping the whole picture stable. Think about sitting outside the observatory. When you and I stare up at the Milky Way, we are never seeing it exactly as it is. We only see it as it was. Alpha Centauri is our closest stellar neighbor, but its glow takes over 4 years to cross the dark. If its sun flared wildly last Tuesday, my screens stay quiet for years, and that is right next door. When I point the lens deeper, the illusion grows. The pale glow of Andromeda takes over 2 million years to hit my sensors. I am recording light that began traveling when early humans were just shaping crude rocks. Push further out, and I catch faint radiation from billions of years ago, long before our solar system was even a cloud of dust. And yet the view feels so alive, the stars shimmer. The clusters burn bright against the black. They look incredibly close, but they are just ghosts. Ancient history carried on slow, patient waves of energy. This exact delay is what makes my job so magical. I am basically a time traveler. When I point my equipment into the deep void, I am looking backward. Every observatory on Earth is really a time machine, digging through forgotten eras. All this cosmic history is visible simply because photons drag their feet. That strict speed limit hands me the past, but it also enforces order across the cosmos in a really elegant way. A star cannot burn a planet unless a ray has time to cross the gap. That is not just physics, it is a protective shield. It stops paradoxes. You and I can sleep soundly knowing the universe keeps things perfectly logical. Without this cosmic speed limit, my field of astrophysics would collapse into chaos. If we could transmit signals faster than light, you could theoretically message your past self. You might warn yourself, skip that sketchy burrito. But if past you listened, there would be zero reason to send the message from the future. These causality loops are exactly what keep my colleagues and me up at night pacing the observatory floor. Thankfully, this ultimate speed cap ensures those paradoxes never happen. You simply cannot outrun causality. Celestial events unfold in order. The past remains behind us, the future ahead. We are not just talking about the flow of time, but its very structure. This governs much more than the distant galaxies I observe. It is woven right into your daily routine. Look at modern communication. When you send a text, you and I rarely stop to think about photon speeds. Yet calling a friend across the globe introduces a faint delay. It is incredibly brief, but our instruments can measure it. That data travels as electromagnetic radiation, bouncing through orbiting satellites or deep ocean cables. These waves pulse at or right near light speed. Even so, Earth is massive. Light still needs a moment. Now consider deep space exploration, when our teams beam a command to a Mars rover. It takes anywhere from 4 to 20 minutes to arrive. The exact lag depends on how our two planets align in their orbits. Meaning if that machine hits a tricky Martian boulder, my fellow astronomers back on Earth will not even know for nearly half an hour. Real-time remote control simply does not exist. The rover must be totally autonomous, making choices alone. The speed of light dictates deep space isolation. Astonishingly, even your late-night streaming service obeys this universal law. Every single pixel of that astronomy documentary you watch traveled from a server, zipping through cables as light pulses, strictly bound by the cosmos's absolute speed limit. While it feels like a hard boundary, I see it as a beautiful cosmic harmony. This steady pace creates a stable universe where every effect clearly follows its cause. The past remains locked, the future unwritten. This structure shapes spacetime itself, turning a chaotic, empty void into a beautifully ordered progression of celestial events. It is a wonderful paradox. The single fastest force in reality is exactly what forces us to wait patiently to see distant supernovas unfold. That gentle delay, those quiet moments of waiting, are precisely what make astrophysics possible. They grant us distance, cosmic perspective, a little room to calculate, and perhaps, just maybe, a peaceful moment to rest. But you and I are curious. Let us pretend for a second that we refuse to accept this absolute barrier. We know all about this speed limit, this strict cosmic law hardwired right into spacetime. Naturally, our first instinct as explorers is to ask, what if we break it? Could any vessel outrun light? It is a deeply tempting thought. Humanity has a long history of shattering boundaries. We conquered the sound barrier. We landed probes on Martian dust. We built massive colliders to shatter atoms. So, what really stops us from discovering a hidden interstellar shortcut? Something faster than 299 million meters a second. Let us examine a strange little concept pulled straight from the deepest theoretical archives. Tachyons, we astronomers dreamed up these purely hypothetical particles to balance out complex math, and they boast a wild trait. They exist strictly beyond the speed of light. In fact, physics says they could never slow down enough to match it. Light speed is their absolute floor. Sounds like a thrill, right? A particle entirely immune to the cosmic speed limit, tearing through the galaxy like a rogue asteroid on overdrive. There's just one massive problem though. My colleagues and I have never actually found a tachyon. Not in underground labs, not floating in deep space, not even hiding within our own data. They are cosmic ghosts, always debated in academic papers, but never actually observed. Even if these tachyons truly existed out there, they would break more physics than they fix. If we harnessed them to transmit data, we would shatter causality. You could literally text yourself in the past. And if you love classic sci-fi films, you know exactly how disastrous that gets. Timelines fracture, histories vanish, and reality simply unravels. So the astronomy community largely agrees. Tachyons are a fun mathematical puzzle, but entirely fictional. They stay tucked away in the theory drawer, but what about other insanely fast phenomena? Let me introduce you to quantum entanglement. It is arguably the strangest phenomenon we study today. When two particles become entangled, observing one appears to instantly lock the state of its twin. Distance means nothing. I could measure a particle here at the observatory, and its twin across the Milky Way reacts in perfect harmony. It feels like breaking the universe's code. You might think this beats the speed of light. Well, yes and no. While these strange quantum links happen instantly, they cannot transmit a single bit of usable data. We simply have no way to control what the final measurement will actually be. So we still can't use it to transmit a message. It is like two observers flipping identical coins on opposite sides of the galaxy and somehow always getting the exact same outcome. Yet neither observer can use those coins to say hello. Einstein himself hated this idea. He famously brushed it off as spooky action at a distance. But in our observatories today, we see that entanglement is real and still won't let us talk faster than light. The cosmos is definitely spooky, sure, but it still obeys the speed limit. Then there is Cherenkov radiation. It is a strange, glowing phenomenon we spot when charged particles zip through water much faster than light itself can travel through that same water. You heard me right, light does not always travel at its absolute top speed. When passing through telescope lenses, glass, or water, it actually drags a bit while bumping into atoms. If a particle beats that reduced pace, it triggers a light shock wave, much like a sonic boom. That is exactly what causes that haunting blue glow we see inside underwater nuclear reactor cores. Nothing is actually breaking the ultimate speed limit of space. It only beats the local limit inside that material. In a true vacuum, light still rules. No cosmic laws get broken, they just bend a little in the water. Let's look at this together. Could we ever build a working warp drive, just like the ones in classic science fiction? Could we literally bend the cosmos instead of flying through it? Well, theoretically, yes. Back in the 90s, physicist Miguel Alcubierre mapped out a way to shrink space directly in front of a ship, while expanding the space right behind it. This clever trick would let a vessel surf a wave of bent spacetime. The ship never actually flies through the void faster than light, but it still reaches its star system faster than a raw beam of light would. It is a brilliant mathematical loophole, but it hits a few massive walls. First off, we would need something with negative energy. That is an exotic material we have never seen in our telescopes and have no clue how to make. Second, even if our labs could somehow engineer it, the sheer energy needed would be absolutely staggering. Planet-sized, really. My colleagues calculated you would need the mass energy of Jupiter just to move a single grapefruit. So for now, warp drives are stuck purely in our imagination. Beautiful for science fiction, impossible for actual engineering. Then we have wormholes. These are cosmic tunnels through spacetime that might theoretically link two far-off galaxies in an instant. Picture them as universal shortcuts or folding stellar bridges. The mathematics absolutely allow them to exist. Yet again, the physics problems pile up fast. Instability, missing matter, temporal paradoxes. It is like building an orbital station out of soap bubbles and blind faith. Even if we managed to force a wormhole open, it still would not be faster than light travel. You are just taking a shorter route. The light still wins the race. We just discovered a really convenient cosmic back alley. So where does that leave us astronomers? Despite all our wild theories and odd loopholes, our observatories have never seen anything with mass move faster than light. Every time my colleagues think we spotted a cheat code, the universe quietly shuts it down with a firm hand and a chalkboard full of hard math. Honestly, maybe that is not a bad thing. That speed limit feels like a frustrating wall for space exploration. Like a locked gate keeping us from the deep stars, but truly it is a cosmic safety rail, stopping the entire universe from collapsing into broken timelines and pure chaos. It gives reality structure. It creates order out in the dark. It offers a kind of quiet serenity, knowing that no matter how wild the stars get, there are deep boundaries the cosmos simply will not cross. So the next time you and I wish we could instantly teleport across the Milky Way or warn our past selves, just take comfort knowing that starlight itself, silent, swift, and completely steady, is moving as fast as physics allows. It is already leading us out there, and maybe that is enough. By now, you probably see the pattern. That light speed limit is not a random rule. It is a massive foundation stone built right into the architecture of the cosmos. But what if it means something even deeper than we astronomers realize? What if that glowing, almost poetic 299 million meters per second is not just a speed cap, but our ultimate key to unlocking space and time? We are going to take a slow walk into the philosophical side of astrophysics. Do not worry, it stays relaxing. You can just stay completely relaxed. One of the most beautiful concepts we study in physics is that light speed is not just how fast a photon flies. It is a universal conversion factor, a literal bridge connecting space with time. That constant, we astronomers just call it c, is exactly what lets us translate light years into time and vice versa. It is the cosmos's own native translator. We see this in Einstein's famous E equals mc squared. In my work, the speed of light acts as a bridge between mass and energy. It tells me exactly how much power is locked inside a given amount of mass. But we also find light speed scattered across relativity, in the math explaining time dilation, length contraction, and the bending of space. Seeing it everywhere is no accident. It tells me this constant is much more than a simple speed. Think of it as a cosmic glue. Join me for a quiet little thought experiment. Picture the universe as a vast woven sheet, spun from both space and time. Not two distinct threads, but one seamless material we call space-time. It sounds like science fiction, but it is entirely real. Under Einstein's rules, space and time are never separate. They link together, acting as one smooth, bending sheet. Moving through space means you are moving through time too. Speed up and time slows down. Heavy gravity pulls and warps both space and time around itself. Here's where light speed matters. It acts as the exchange rate between space and time. Just like swapping euros for dollars at a bank, except here I am trading meters for seconds. This is why astronomers measure the void in light years. That's not measuring time, we are measuring pure distance. A light year is just how far light drifts in a single year. Using a clock to measure space shows me how beautifully locked together they really are. So when my peers and I say nothing outpaces light, we mean nothing can break the bond between space and time. The speed of light sets those rules. It's the thread holding our reality together. I find a deep comfort in that, knowing our universe has this built-in, quiet stability. No matter your location, no matter how fast your telescope moves, light speed stays exactly the same. It's the cosmic anchor that balances my equations, keeps the cause strictly before the effect, and ensures the cosmos behaves, even near black holes or galactic cores. Truly, we do not even view it as just a speed anymore. When doing the heavy math, many physicists simply set the speed of light to 1, just the number 1. Not out of laziness, but for pure simplicity. Do that, and suddenly space and time stand on completely equal ground. We measure distance and duration with the same units. The math becomes beautifully clean. The cosmos just neatly tidies itself up. Now, let's explore a much stranger idea together. What if space is not built just for light to move, but built entirely around the speed of light itself? Think of it this way. When a photon travels, it feels absolutely no time. If you were a photon, your birth from a star and your death hitting my telescope would happen instantly. There is no ticking clock within a light beam. From its point of view, time never even happens. It sounds wild, I know, but relativity proves it. Faster movement means slower ticking clocks. Hit the speed of light and the ticking stops entirely. That beam only exists in pure, constant motion. It's never resting, it simply cannot, which leads me to this lovely truth. Light does not just cruise through the void. It shapes the cosmos as it flies. That speed is not a choice the photon makes. The universe demands it. Today, astronomers and scientists even base our simple human rulers on this exact speed. Since 1983, we have defined the meter by tracking how far light flashes in a tiny slice of time. A meter is the distance light crosses in 1/299 millionth of a second. That's not just poetry, that is absolute precision. Light is the cosmic ruler we use to measure all other rulers. It's our baseline for space and time. To me, that is the most grounding thought. Looking out at a dark, strange universe full of invisible matter and chaos, I find comfort in something beautifully fixed. Light speed is a cosmic anchor you can build a whole world around. We literally do just that. So tonight, when you see a candle flicker or catch ancient starlight through your telescope, remember this truth. You are not just seeing brightness, you are watching a law of physics, a message from the geometry of space-time. It reminds me that while our universe is immense and deeply mysterious, it is also wonderfully, quietly consistent. Light does more than illuminate the dark, it sets the rhythm for the stars, and on a quiet night. As old photons from distant stars wash over you, imagine the void whispering to us in its own gentle language. Steadily at light's exact cosmic limit. You and I have seen tonight that light speed is no mere footnote in my textbooks. It's the pulse of the cosmos, the deep stitch holding space-time together, and the steady metronome keeping our reality ticking. You and I spend a lot of time looking up, but the speed of light isn't just drifting between galaxies or reflecting off distant stars. It is woven right into our everyday lives on Earth. Even if you have never flown a spacecraft or built a backyard particle accelerator, though if you have, I am seriously impressed. You still live in a world shaped, defined, and quietly orchestrated by the speed of light. Let us start with something familiar. Your smartphone, yes, that little pocket device you are listening to right now. Every time you tap the glass, stream a video, or send a sleepy message to a friend, you are harnessing the raw power of starlight. Specifically, light beaming through fiber optic cables. These thin strands of glass and plastic act as the backbone of the entire internet. They snake across ocean floors and continents, forming a worldwide web that moves data at almost the exact speed of light. When a web page loads, you are not simply waiting for a distant server to think it over. You are waiting for pulses of light, tiny flashes of ones and zeros racing through those cables, bouncing across routers until they finally reach your screen. While light moves through fiber a bit slower than it does through empty space, roughly 2/3 the pace, it is still astonishingly fast. We are talking hundreds of thousands of kilometers a second. That is how your cat videos, weather forecasts, and sleep playlists show up almost instantly. But those fiber optic lines are not just shuttling data around, they also help keep perfect time. As an astronomer, I love pointing out that one of the technologies most dependent on the speed of light is the Global Positioning System, or GPS. When you use your phone to find a local bakery, it connects to at least 4 different satellites quietly orbiting our planet. Every single satellite beams down a signal with a timestamp precise to the very nanosecond. Your receiver compares when those signals arrive to calculate your exact location. It is sort of like asking 4 distant friends how far away they are and using their answers to pinpoint your exact spot on a map. But here is where you and I look deeper. To make this work, we must account for special and general relativity. The exact physics principles we have been gently exploring together. Because those satellites move fast relative to Earth, their onboard clocks tick slightly slower thanks to the rules of special relativity. At the same time, they float higher up in Earth's gravity well, causing their time to tick a bit faster due to general relativity. The cosmic result, without correcting for both of these strange effects. Your navigation would drift off by several kilometers every single day. Because of Albert Einstein and the rock-solid speed of light, your phone can accurately tell you which street to turn down for your morning coffee. Let us zoom all the way down to your own eyes. Human vision perfectly captures light's beautiful behavior. When you look out into the world, you are watching photons bounce off physical objects directly into your pupils. Those tiny particles of light travel through your cornea and lens, hit your retina, and spark chemical reactions inside your rods and cones. Your mind then grabs those electrical signals and paints a vivid, colorful picture of a tall oak tree, a fading sunset, or your oddly dramatic house plant. This entire cosmic process depends on how fast light moves, how it bends through different mediums, and how it sparks the atoms inside you. Even perceiving depth and motion comes down to a tiny fraction of a second delay between light reaching each eye, letting your brain compare the twin signals. And speaking of bending light, consider refraction. The way a beam slows down and shifts direction the moment it enters a thicker material. This creates that illusion of a bent straw in your water glass, or the watery mirage shimmering on a hot summer highway. It is the physics powering my observatory telescopes, reading glasses, and camera lenses. Whenever you capture a photo or open a book with your glasses on, you are relying on centuries of stargazers studying how light travels. Even your kitchen microwave owes its life to the electromagnetic spectrum. Microwaves are literally just a lower frequency form of invisible light. They bounce around inside the metal box, forcing the water molecules in your food to vibrate and heat up. Without this invisible slice of the spectrum and our deep grasp of light waves, reheating your late-night leftovers would be impossible. Let us take a cozy step over to telecommunications, your favorite late-night radio station. That is just light waves too. Radio waves sit on the same electromagnetic spectrum, just stretched into much longer wavelengths than visible colors. They cross the vacuum of space at the exact same speed, letting your car blast music on lonely night drives, television broadcasts, local Wi-Fi, and your Bluetooth. All of this is just radiation zipping through space, obeying the exact same physics you and I see in distant starlight. Now, let us peek into medicine. X-rays, those glowing, ghostly images of your own skeleton, are simply high-frequency light waves. They slide right through soft tissue, but hit denser material like bone. That contrast is exactly what paints those eerie skeletal snapshots. And MRI machines, even without using visible light, rely on electromagnetic fields to map out stunningly detailed landscapes inside your own body. Put simply, light and its invisible family of waves run quietly behind the scenes of our modern world. It lets us communicate, navigate, cook, stream, and my personal favorite, study the stars. And speaking of the stars, I want you to remember that everything we know about the universe beyond our solar system was delivered to us by light. Instruments like the Hubble Space Telescope catch fragile photons that have crossed the empty dark for billions of years. To me, these ancient beams hold encoded secrets about distant galaxies, dying nebulae, black holes, and the early cosmos. We decode their whispers simply by reading the color, intensity, and hidden spectrum. A tiny stretch in the wavelength, what we call a red shift, shows me exactly how fast a galaxy is rushing away. A subtle dimming tells us an alien planet just crossed its star. And a faint glow lingering in the background might just be a lingering whisper from the Big Bang itself. It all makes sense because light follows the exact same rules everywhere. Whether it is a photon hitting your telescope lens or starlight from a galaxy 13 billion years away, it travels at that one unwavering speed. So tonight, when you look up at the moon, just take a deep breath and marvel at what is really happening. A quiet, graceful dance of photons, invisible fields, and perfect universal constants. The tireless motion of light racing through our world at 299,792,458 meters per second. This light is not just a cosmic wonder, it is right there in your room and in your eyes. It is the silent engine of everything. Picture a single beam of light drifting across the deep void of space. Out there are no planets, no stars, and no gravity tugging at it. Just one lonely photon, gliding smoothly through the cold vacuum, never speeding up, never slowing down. Massless and fuel-free, it exists in motion at the only speed it knows, 299,792,458 meters per second. As an astronomer, I find that serene image is so much more than poetry. It is a raw glimpse into the universe's fabric, because this humble little beam of starlight is doing way more than just traveling. It is playing a part in the grand cosmic symphony, a quiet dance of energy. And time shaping reality itself. Come with me, let us look at one of the most awe-inspiring pieces of astronomical history, the cosmic microwave background. It is not just some fancy label. This is the oldest light in creation. It has been drifting through the dark, completely undisturbed, for almost 14 billion years. This faint, uniform glow fills our entire universe, gently bathing everything we see, and it does not come from any stars or galaxies. It is the fading echo of the exact moment the universe turned transparent, roughly 380,000 years post-Big Bang, when atoms finally formed and photons roamed free. Before that moment, the entire cosmos was a dense fog, opaque, deeply chaotic, and boiling hot. But once neutral hydrogen finally formed, light could finally move without endless collisions, and so it did. It rushed out in every direction, an ocean of ancient radiation now stretched by an expanding cosmos into soft microwave whispers. When we astronomers measure this glow, we are literally catching photons that have been flying since the dawn of time. These tiny particles of light have never once rested. They cross the entire cosmos just to softly hit our telescope detectors and show us exactly what the universe was like back then. That is not just history, that is pure cosmic archaeology, but our story does not end there. Light does more than show us the distant past, it binds together everything we experience on Earth right now. From how massive suns burn to how tiny atoms react, light participates silently in every single process. Take a look at photosynthesis, for example. It is the deep engine fueling life on Earth, and it all begins the second sunlight strikes a simple leaf. Starlight hits those chlorophyll molecules, exciting the electrons and sparking a cascade of reactions that lock energy into solid chemical bonds. Flora uses that solar energy to bloom. Animals feed on those plants, or they hunt the creatures that grazed on them. And so this beautiful biological chain continues. Without starlight, there is zero photosynthesis. Without that process, green life vanishes. Without plants, well, let us just say human survival gets incredibly bleak. In a very real, scientific sense. Every single meal you consume traces back to a photon born in our sun, and flora isn't alone in soaking up this radiant energy. You and I are built to capture it too. Our human circadian rhythm, our deep internal clock, is completely governed by the light of the cosmos. Even for us astronomers, shifting sunlight sets our daily rhythm of rest. And mood, that first morning glare tells the brain to halt melatonin, the chemical keeping us asleep. When dusk falls over the observatory, that melatonin surges back, gently pulling you towards sleep. Right now, listening to these quiet cosmic thoughts, your body tracks the dimming light in your room, shifting its rhythm to match the turning Earth. But in my line of work, light's true power is connection. It bridges my telescope to distant suns and ties moments across eons. It is the great messenger of space. Whenever I gaze across the control room or deep into the night sky, I am reading messages carried on ancient waves, decoded by the human mind. Light is the cosmos speaking, and like spoken words, it holds dialects, unique wavelengths sharing very different stories. Some spectra reveal the exact chemicals swirling inside remote galaxies. Others scream of gamma-ray bursts, the most violent detonations in the known universe. Some beam the infrared heat of a baby star. Others scatter rainbows across earthly puddles, exposing the quiet math of how waves bend and interact. For astronomers, this wide spectrum is our greatest tool. It doesn't merely prove a star exists, it explains how the star breathes. Passing a simple beam through a prism exposes a hidden symphony of color. Catching a supernova's flash let me trace the very fingerprints of heavy metals forged inside a dying star. And the beautiful part is, we've built the tools to listen. Through enormous radio dishes, we pick up cold hydrogen whispering. With X-ray lenses, my colleagues and I map the fiery bones of galaxy clusters. Using infrared sensors, we peer straight through dark dust to watch stellar nurseries ignite. We've even built sprawling detectors tuned to catch ripples in the fabric of spacetime itself. A new cosmic messenger answering what those ancient photons first promised. My nightly observations prove the universe isn't a frozen, empty void. It is a vibrant network buzzing with signals, ancient stories, and endless light. It shows me we aren't just isolated watchers. Sitting at the telescope, I know we are bathed in the cosmos, built by it, belonging to it. The atoms resting in your body were cooked in stars burning billions of years ago. Their light drifted across deep space, grazed gas clouds, and sparked brand new worlds. That identical cosmic cycle birthed the carbon in your cells, the calcium holding your bones, the iron in your veins. You and I are truly made of old star dust, delivered by the grace of light. So this tireless traveler, a photon with zero mass and no ticking clock, does more than just fly. It tethers the distant past directly to our telescopes today. It strings atoms together with vast galaxies. It lets us observe and finally understand. Staring into the unknown dark, light remains our most loyal guide. It's not just impossibly fast or fundamental to physics, it feels profoundly familiar. It's the subtle hum translating space into a story, filling the blackness with meaning, whispering across the cold void to say, I am still shining. So tonight, as you lay back and let your mind drift among the constellations, remember that even in the pitch black, ancient light is rushing toward your eyes, and just like that, we float gently back to where this observation began. You and I set out to crack a simple question. Why does light have a speed limit? We've traced paths of scattered photons and danced with shifting electromagnetic fields. We've mapped the faint, ghostly static of the cosmos, charted bending time and stretching space, watched physics warp clocks, and seen stars speak in fading beams. We've jumped from fiber cables to deep sky objects through your own eyes to the quiet microwave background. The conclusion I've found in all my years looking up is beautifully simple. Light moves at a constant speed because our universe is literally built to be molded by it. That limit isn't just about speed. It's the bedrock structural rule keeping everything from collapsing, tying tiny atoms to the widest sweeping galaxies. It's a physical law you simply cannot outrun, and honestly, I find deep comfort in that. That fixed velocity gives the cosmos order. It creates time itself and gives astronomers something to measure. It delivers our history, paints sunsets, and brings the warmth of distant stars to a cold dome. We don't need it traveling 1 second faster. It is entirely perfect the way it was designed. Now, as I power down the observatory equipment for the night, let me ask you once more. Where on this rotating rock are you resting tonight, and what time does the clock show exactly where you are? Are you tucked into bed with Orion outside your window, or maybe across the globe, watching the sun's first rays scatter through the morning atmosphere? Wherever your coordinates lie, whatever the hour, thanks for exploring the night sky with me. If our session helped you relax or sparked some quiet cosmic wonder, I'd deeply appreciate a like and a quick tap on subscribe. It guides other stargazers right here to our calm little corner of the universe. And if our cosmic journey kept you awake, well, at least you learned something fascinating while waiting for sleep to finally find you. Until our next observation, rest well, and may your dreams orbit at just the right velocity.